Howdy. Let's do some of this homework. Let's start with chapter 15. That's one that is next on our list. So, starting off, checking out these. I've got originally here some amino groups. So I've got an amine here. We want it to have the lowest possible number. So this is a primary amine. It's got one carbon. So it's on a secondary carbon, but it's a primary amine. All right. It didn't ask me about that, but I'm sure there'll be questions on it. So 1, 2, 3, 4, 5 carbons. And so that would be pentane. We drop the E, add amine, and there's nothing on the end, so 2-pentanamine. All right, that's not too bad. And then this one, remember, it doesn't have to be attached at 1 under IUPAC. 2, 3, 4. So this would be 2-butanamine, and it has a methyl group, so on that end, N-methyl 2-butanamine. Alright, so dash between the methyl and the 2. Alright, okay. Number 3, it wants the common name. Alright, so common names, it's going to end with amine, so I have an ethyl and 2 methyls, so it'll be ethyl dimethyl amine. And the unfortunate thing about amines is it's all one word. Alright, so this one has one big long one. 3, 4, 5, 6. And so this would be hexyl amine. And that's pretty straightforward. So while I'm here, look at these. This is a secondary amine, tertiary amine, a primary amine. Alright, easy enough. So let's do this next page. It says classify each as primary, secondary, tertiary. So we get some practice. Dibutylamine. So a butyl, 1, 2, 3, 4, and then our N, 1, 2, 3, 4, 1, 2, 3, 4, and so then there'll be an H here, so that we have 3 bonds on this, and dibutylamine is secondary, so that's secondary. 2-methyl 2-heptanamine. Now we got IUPAC. So this first one was common. This is an IUPAC name. So 1, 2, 3, 4, 5, 6, 7. And at 2 is a methyl, and at 2 is an amine. Alright, now notice there's nothing that says N. So on this one, I have that's a primary amine. Even though it's a tertiary carbon, it's a primary amine. Alright, so tripentylamine. 1, 2, 3, 4, 5. And we got 3 of these. And so there's no room for any hydrogen, so it's got 3 carbons. That's tertiary. And ethyl methylamine. Ethyl methyl would be secondary. Okay, not too bad. Give the IUPAC name for this. Oh, we got some amides now. Okay, so don't forget amides. You've got carboxylic acid side, and you've got your amine side. So 1, 2, 3, 4. Butanoic acid. Butanamide. Alright, so drop the oic acid and add amide. 1, 2, 3. And so we have an N-propyl butanamide. This one, 1, 2, 3, 4. That's just butanamide. And this one, 1, 2 is my parent. So IUPAC, that'd be ethanoic acid, so that's ethanamide. And I've got 2, so I'm going to put N, diethyl ethanamide. So this one asks me to go ahead and do the common names. Okay, so let's get rid of that, and we'll just get rid of everything. So common names. So this one, 1, 2, 3, 4 would be butyric acid. And so that becomes butyramide. And in purple. And this is just butyramide. And this would be acetamide and N diethyl acetamide. So let's see if I can pull this naming up for us. So the common name is actually really very similar here to our sorry, I got wrong mice, wrong everything. So common names really similar to IUPAC for the amides. Makes it much easier. Let's see. So it asks us to classify 9, 10, and 11. So I'm going to go back and look at that picture again. 9, 10, and 11. And be careful on these, because when I classify this, I'm looking at the carbons attached. So that one is secondary. This one is primary. And this one is tertiary. Just the carbons on the nitrogen. And it's that simple. Okay. So then, common name for question compound 11. Oh, that's where we're at. Okay, we did that. And that's the end of 15 homework. All right. So IUPAC and common, they're really not too bad. Dropping the oic acid or the ic acid. And the hard part for most people is to remember the root is always based off of the acid part. All right, so don't forget your 5 common name acids. So let's see if I can pull up chapter 16 homework. So here's chapter 16 homework. Ooh, carbohydrates. All right. So it says refer to this carbohydrate, and so it's going to ask me aldose, or ketose, hexose, 3 and 4, D and L, and then how many carbons. Okay, so we can knock out all of those. So I'll start off up here. This is telling me this is an aldose. Let's see, then the number of carbons. 1, 2, 3, 4, 5, 6. So that's a hexose. Alright, D and L, I'm looking down here. D is on the right, L is on the left, so this is L. Okay, and then it wants to know how many chiral carbons. Now we can spend a lot of work, but as long as these things, the top and the bottom, as long as the top and the bottom are different, and these things are not the same on both sides, right? So as long as no side has two H's, so if I were to write that, it'd have two H's. That's why it wasn't drawn with the cross. So I just count these: 1, 2, 3, 4 chiral carbons. Okay, so that was not too bad. Very symptomatic of what we would expect to see on the test. All right. So next set of questions, look at these drawings, and immediately I notice something, but it's only because I'm looking for it. The bottom and the top are actually the same, and so if I see those be the same, I have to worry about this idea of meso. So meso is when you can draw a line of symmetry. And so we'll look and see if there's any lines of symmetry in any of these. And I don't see one because I got an OH and a BR. So an OH and a BR, I don't have to worry about any lines of symmetry. No line of symmetry, no line of symmetry there. So now I'm looking for, we got an A, B, and C. We got meso. We know it's not meso. Diastereomers and enantiomers. So enantiomers are mirror images, and they're non-superimposable. Alright, so mirror images, can I draw a line between and have these equal? Yes, I can. Yes, I can. And if I flipped it around, if I took this and spun it, the BR would end up at the top. And so those are enantiomers. That is 5 is 1 and 2 is A. So 1 and 2 is A. And 2 and 3, so I'm looking at these, they're not mirror images. Okay, and if I spun it around, it would also not line up. And so 2 and 3, and we'll see this a lot, you've got two sets, if we look real careful, enantiomers and enantiomers. Any one out of this set with any one out of that set would be diastereomers. So this would be B. Let's see if it asked about 3 and 4. It did ask about 3 and 4. And so 3 and 4 are enantiomers. Okay. Okay. Kind of the giveaway is how we ask about these, but you really got to watch for these being a line of symmetry. So I bet the next question's got some kind of line of symmetry. Again, giveaway, top and bottom are the same. Oop, there's a line of symmetry. So this compound, these two are the same. Those two are the same, and so they're meso. So 1 and 2 are meso. And 1 and 3 over here is diastereomers. And the next set they ask about will be 3 and 4. And so these, if I spun it, this OH would end up on the bottom. And so they are mirror images. And so 3 and 4 are enantiomers. Okay. And that's it for that homework. Oh man, flying through it. Flying through it. Alright. Let's see what else we have. Oh, the big homework packet. 16 to end. Alright. Now we are talking 16 to end. So this is continuing 16 through estrogens. Okay, I guess part of this is getting cut off. Alright, so we're looking at this structure, and this is a protein structure. It's got some amino acids, and it's going to ask us to do these. So let's go ahead and pull up our amino acids. And so I'm looking at this table, and there's actually two parts to it, the top and the bottom. I don't know, I guess we had some copy paste issues there. So this is a handout. I'll give it to you. It's usually attached as part of the test. A good place for it is the old test. There's a practice test online for you. So I'll be looking at this, and this tells me these R's. But I have to also visualize my picture. Let me get it to where you can see that picture. H3N HR, and I get my, I'm drawing this as a zwitterion, which we see here. Okay, so I can look over at my table, and I'm going to match these. So first thing I'm going to do is, before I even start, I'm going to come over here and I'm going to go NCC, and I'm going to draw a line. NCC, and I'll draw a line. NCC, and I draw a line. NCC, and I draw a line. NCC, and I draw a line. NCC. And so it says the R group on the N-terminal amino acid. And so the N-terminal is over here on the left. It's the one that has the N, so that's what I'm looking. And I want the R group, so I'm visualizing this picture. It's that middle C. They're talking just about this, and they want to know, is it positive, neutral, or negative? Okay, so I've got to be careful and see if there's a charge here. And when I look closely at this on my screen, on there it's really tough to see, so I'm going to look closely here, and there is 3 bonds, and there's no charge, and so this is neutral. Alright, and so don't look up here, we're just looking at the R. Alright, then it says how many amino acids are contained in this structure. So I can count the nitrogens going across, or I drew my lines. So 1, 2, 3, 4, 5, 6. So there's 6 amino acids. Then it asks me the structure is, and it wants to know the charge. Alright. So I'm going to get rid of my drawings here. And I'm just going to keep a count. So I'm going to put a plus and a minus. Alright. So 1 plus there. There's a plus. And there's 2 pluses. And 3 pluses. Alright. And minuses. There's 1, 2. So 1, 2. And 3. There's 1 over there. So I've got a plus 1. Those cancel out. Plus and a minus. Those cancel out. A minus and a plus. Those cancel out. So I come over here. It says, what did it add up to be? It's a 0 charge. Okay. So then, now they could have, they didn't, but they could have said, hey, what is the names of these? And that's where we'd have gone to our chart. Alright, and so let's go to the next question. Oh, that's a big long thing, but it's an example of what kind of structure. Alright, well, listing those out, remember we've got 4 structures. 1, 2, 3, 4, and that's my primary. So primary is just our list of the proteins. Secondary, that's where we get our helix and our sheets, and that's how it twists or it folds in on itself. And these are our large secondary. I hate to use that word because it's a tertiary. It's what we're talking about. Large folds. I don't know if we'd call them secondary folds, but whatever. And then 4 would be, it would include its structures, the main keyword we're going to look for. So that's a primary. So we have primary, secondary, tertiary, quaternary, and prosthetic. Prosthetic's not making sense, so it's primary structure. And they want to know, ooh, here's another one, how many are contained in this structure. Alright, so how many are contained? So in CC, that's what we're doing. NCC, 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 NCC. So how many are contained? 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay. Now it is some kind of peptide. So peptide. All right. It's talking about this peptide bond. All right. But how many proteins are there? So monopeptide would be 1 protein. Dipeptide would be 2. Tripeptide would be 3. Oligo would be a few. That's not what we got. So it's oligo. Alright, you could have done polypeptide, but those are much bigger. So I won't have you choose between oligo and poly. So that's not a problem. And then it wants to know its charge. Oh, that can be a little bit tougher. So I've got 1, 2. I have 2 positives. I have 1, 2, 3 negatives. So its overall charge 1 minus. Alright, and the argument on, sorry, my glue is wearing out. Okay, the N terminus, so that's here, the component of, and it wants me to identify it. Alright, so we're basically identifying this, and it has CH2SH. So I'm going to go to my table, and I'm going to find CH2SH. CH2SH, not on that sheet. Up, CH2SH is CY. So I'm going to go ahead and write that CYS. And I'm just going to write that right up here. And then I want to check, that's going to be the answer to that question. But then it wanted the C terminal. So let's go to the C terminal. Wait a minute. And then it asks us, it does ask us eventually to go ahead and do it. So let's just go ahead and do that. Alright, so we're going to go CH2, C carbonyl, and the key is there's only one CH2. There's 2 of them that are like that. So glutamate looks like that, but it's not quite. And this is aspartate, so that's ASP. Alright, so don't fall into that trick. So aspartate has just that CH2. Alright, this is just an H, and that is on this side, and that just R is an H is hidden from me. I think it's glutamate, but it's glycine, GL. And then I got CH2 benzene ring with a phenol. That's on this next sheet. Phenol, TIR. And now I've got, you see the difference here. That was aspartate. So now we're looking at not aspartate, but it's this huge glutamate. There's our glutamate, GLU. This has an amide at the end, ASN, asparagine, ASN. And this has this NH and another NH, and that's all over the place. That's histidine. Alright, and it's got flipped around version of histidine, but it's the same. And then, oh, I got a CH2, and then, so I got isobutyl. Isobutyl, so let's double check that. So this one has a sec butyl. This one has 1, 2, 3, 4 isobutyl. That's LEU. And so that is this CH2CH, CH3, CH3. Both of those attached here. So that's LEU. Alright. So having all of those. So let's see, does that match any of these? So first off, so the C terminal was LEU, and if it was from a living organism, so we said, so this question, sugars are D, proteins are L. Alright, so this one, it should be L, it would be C. Okay, the primary structure, given structure, so let's see if we get all these right. We got cysteine, aspartame, glycine, tyrosine, glucine, histidine, leucine. Are some of these wrapping around for this 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4. So B is what we're getting. Key bin. B looks like our answer. Alright. And let's see what we got next. Alright, so this one, off of that homework, we would just match them. So if I went back, we said it was C, and you could take those names and write them out full. Really don't line up. Glycine, tyrosine, glucine, tyrosine, glucine. B on this one. Alright, so there's B. Alright, and then, okay, so the leucine residue. So it asked me to look at leucine. So let's go over here and look at leucine. So I'll find leucine, that's down here. And it is CH2, that's that isobutyl group. And so an isobutyl group, it can be nonpolar hydrophobic, it can be polar, it doesn't have a charge, and it doesn't have anything but carbons and hydrogen, so it's a nonpolar. Okay, and then it wants us to identify these, and they even have these little colors shaded here, so nice and fun. So, oh, it's even the class, so it's an SER. So if I had trouble reading it off of this, I can find it online. SER is a CH2OH, and then I've got 309, which looks like that with my zigzag. Those have OHs, but no charge, and so they will be neutral polar, D. They are neutral polar. Okay, identify those the same way. Let's see now. Next, looking at this stuff in green. And that one's a little hard to read. And leucine and val. So having a hard time reading those. So val and leucine. Okay, there's no charges, and there's nothing but, so that's A. But carbons and hydrogens. Looking at this one, so it says it was histidine. So let's draw that a little better. So looking at histidine as CH2, there's my zigzag, and then histidine has this five-membered ring. And what's key about this is this has a plus charge. Now on this one, it's hard to see. It has a plus charge, and it should be showing a plus charge. Okay, I agree on the homework. That one's tough to see. They should have a plus charge. So that histidine. So what class of compounds? So positively charged right there. This one is aspartate, and it has a negative charge. I can see the negative charge there. So that's what you're looking at. We'll have a little bit bigger pictures, hopefully. So no problem. And then use the structure on the next page to figure out 17 through 20. And that's this thing over here. And it wants to know, is this a monosaccharide, a disaccharide, a polysaccharide, or a carboxylic acid? Oh man. But I'm looking up here. That's a sugar. Yeah. So that's a monosaccharide. There's only one in there. I've got a peptide bond. I've got a lot of stuff going on. They might ask, hey, what kind of drawing is this? So this is Hawthorne. Alright. So we can find all kinds of, we had Fisher before. This is Hawthorne. We got all kinds of stuff going on. So I'm going to look here. If you can see the green. And that tells me if it was aldose or ketose. This was a ketose, so that's keto. I can count the carbons. 1, 2, 3, 4, 5. Don't forget that one. 6. It's a ketohexose. So that's F. Alright. Then I'm going to look at this OH. It is opposite CH2OH. They're trans. That is alpha. Alright. Beta is when they're cis. The Carl centers. So it's got 1, 2, 3, 4. I notice if it, for instance, when we do deoxyribose, we lose this OH and it's just an H. We lose that Carl center. This one has 4 Carl centers. Let's see, what else do we got? Alpha and beta, we said it was alpha. Okay. Then it says 21. Oh, must be a different chapter because we had different font. Fatty acids generally contain even number of carbons. And it wants to know this formula. Okay, so I'm just going to count the carbons. I've got 14, 15, 16 carbons. So 6, we've got to start with hexa and then deca. So hexa and deca, that's 16. And then oic acid, hexadecanoic acid. Alright, if I were to go through, there's no unsaturation except for the carbonyl. And so this would be 19, this is 20, there's 18, this is 16. So if I'm looking at that, how would I describe it? Does it have an odd number? No. Is it unsaturated? Does it have any double bonds? Well, nope, not. They're all CH2s. So nope, it's saturated. Now oil. Okay, so we got oils. We're going to see polyunsaturated, and maybe, yeah, usually we say it's a polyunsaturated. Sometimes you can get by with the monounsaturated, but saturated fats. Oh, all right, and then we're looking at this one. Uh-oh. We got a lot going on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. Octadecanoic acid. Alright. We've got double bonds at starting at 6, at 9, at 12, and 15. And they're all cis. Now, this would be, I need to change. Ooh, we got a change in this. So it's decanoic, but it's tetranoic. Watching, yeah. Let's see if I have a pretty picture of it. No. That's the wrong one. That's the wrong one. Tetranoic. Yeah, decatetranoic. That's what I thought. Okay. That's that. Back to our tetranoic acid. It's a mouthful. Octadeca, because you're going to want that. Deca. So you don't want that T there. Tetranoic acid. So you can see why IUPAC would separate it. And tetra, and then I have enoic, 6, 9, 12. We like numbers in the front. You put them in order. 6, 9, 12, 15. And then you gotta say that each one is cis. Oof. Put it in the blank. Yeah, good luck with that. Alright, so octadecatetranoic acid. That's a lot harder than that. Alright, so all that. Chemical description, that's what we really care about. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, just so on and so forth. It does have even number of carbons. So it's got that. Unsaturated fat, definitely. That's, man, that's, it's going to be solid. No, that's going to be a liquid. So we can go with even carbons, but chemical description, really care about factor that's unsaturated fat. Luckily, it's all cis. Remember, trans fats are really bad. So this is, now here's this omega here. So my omega starts at the end. So 1, 2, 3. So this is an omega 3. Wait a minute. Omega doesn't even go to saturated, so don't use those. And it is, in fact, an omega 3 unsaturated fat. Now, wait a minute. 4, 5, 6. Is it an omega 6? You bet. It's both of these. Now, usually you would consider this an omega 3 because that's the first double bond, right? But it is also an omega 6. Man, who came up with this? All right, and let me see our pretty picture down here. Good, I had that in C and D. All right, good. And this requires how many moles of gas in a hydrogenation reaction using a nickel? In other words, H2 and nickel. All this is how many double bonds and 1, 2, 3, 4. All right. Now I didn't give you the option of 5, and the reason I didn't is because some people will get confused and they also want to do the carbonyl. So what we care about is these 4. They actually go fast, and then you can do the carbonyl if you really forced it. But we won't actually worry about that. Okay, so here's this same kind of reaction. So they're asking about this reaction. 1, 2. We went down here. We got rid of all those double bonds, but we're going to keep the carbonyl. So we lost the 2 double bonds. What kind of name is this? That's a hydrogenation or a reduction. Same question we saw before. Okay. A saponification would be making soap. So we break an ester. Esterification, we make halogenation. We're either adding halogens or we're substituting to put halogens on. There's no halogens here. So we did H2 platinum, palladium, or nickel as a catalyst. So the starting material, 1, 2, 3, 4, 5, 6, 7, 8. It's an omega 6 or an omega 9 unsaturated. So don't ever worry about the saturated with omegas. Omega 6D. Omega 6 saturated. Alright, let's see what else we get. What did we make? We made a saturated fat, but it was no oil, a solid, unsaturated, solid, or oil. Alright, so saturated plus the solid, and then mono unsat and poly unsaturated. Those tend to be oils. Alright. Oh no, a screen is freaking out. So I'm looking at my vegetable oil, and so this is what I'm thinking about those oils. Apply my crappy piece of paper, and we will reset my camera here. Reset my camera. Ta-da. In technology, great. Alright. So under what conditions will this take place? So we need a catalyst, and we need the moles. So they're doing, so we're still referring to 29, yep. I'm still referring up here to this reaction. So it took 2 moles of hydrogen. So 2 moles of H2 with a nickel catalyst. C. Okay, so that'll be C. Okay, excellent. So before, so we said the product will be a saturated fat, which will be a solid. Okay. Let's see, we got a whole new reaction here. So I've got some reaction. We're hitting it with some heat and some base, and we're deprotonating it. Oh, look, this is the process to make soap. Alright, so this is saponification. And it says what is acceptable name for this? Saponification would be it. Acid hydrolysis, if we did that in the presence of an acid, we could also break it, but that's not what's going on. Esterification would be reversing it. Hydrogenation, we don't have the right stuff for that. What are we missing? Well, when we do this, we have to add the water back. We took water off to make this bond. And so what are we missing? We're missing water. Alright, the triglyceride is what we started with, and this is the process to make soap. And alcohol is one of our products, and that here we'll be getting glycerol back, and the base is shown on there. So take a triglyceride, add some water, add some base, doing a big thing. All right. Ionic products. So the ionic products we get over here, that is soap, fatty carboxylates. Then it said esters. Nope, we broke apart as unsaturated fatty acids. They're all saturated, so that doesn't work. And saturated fatty acids. Well, this is actually soap. This is fatty carboxylates. All right. Okay, and then we're doing this reaction. So we added that. That's an esterification. So it says, what is the name of the product? Okay, so I'll come back over here. I have 20. So 20 was that icosanoic. And we had a methyl. Yep, so methyl, the first icosanoate name just like that. So that'll be A. Alright. Notice when I did that the acid part was the parent and this was a side group. Alright, so that's my methyl, and notice it's a separate word, just as if I was naming the sodium in the previous one. I'll come all the way back here. If I was naming these, this had 14, so tetradecanoic acid, but this is sodium tetradecanoate. Alright. Oh, no, wait a minute. What is acceptable name for this reaction? So this one is an esterification. We made an ester. What are we missing? So I need an acid catalyst. And so, let me see, product would be an acid catalyst. What is the name of the reactant? This reactant had 14, so that'd be tetra. What do we got going on here? Hang on. I got methanol, 33 to 55. Go to that reaction, and counting wrong. Oh, it's an 8. Oh, okay. Hang on. It's 18. No, that's counting 13 or something. Alright, so 18, so that'd be 20. There's some methyl icosanoate. There, methyl icosanoate, or A. And then, so name of the reaction, icosanoic acid, 20. Alright, not the 8, it's going to be the acid. Alright, so now it says, let me refer to that for the 50 patent. I don't know, something's wrong with that. Alright, so lipids yield more than twice the amount of energy broken down by the body compared to the same amount of carbohydrate. So therefore lipids are, let's see, hydrophobic, I don't know how we're going to get that from there. Low melting point, I don't know how we're going to get that. Good insulators, they're okay, but efficient sources, that's just critical thinking. Efficient sources of stored energy, okay. Define enzymes. What role do enzymes take? Enzymes are catalysts. Catalyst is their role. Vitamins, you get uptake from the body. I'll let you look that up. They are used in all kinds of things, and mostly making coenzymes. RNA codons. We need a handy sheet for this, so I'm going to go to this sheet and I will go to this thing. If I zoom in, that's what it looks like. Alright, so I'm going to be referring to that, and the key to this is split them in three. So I'm going to go ahead and do that. I'm going to throw this pin away, and then I'm going to 3, 3, 3, 3. I better get a full set of 3 at the end, or I mess it. There we go. Alright. So AUG, so I'll find AUG. AUG. AUG says start. Alright. G is start, which is MET. And then we got CCA. CCA is PRO. Let me get rid of this pen. Type in some better. Right. We had MET, PRO, CAA, GLU, is glutamine, CGA is proline, double check that. No, it's not. That doesn't seem right. CGA is arginine. CGU, so CGU is arginine. You'll notice some of these codes, multiple codes will give you the same one. Let's see, so GUG, GUG. Valine, CUU, CUU, so I go to the C's, I go to the U's, CULEU, UAA, so if I'm not U's, if I'm not A, UAA says stop, and that just tells me, so that's what signal, net, pro, arg, arg. Alright, let's do the next one. Alright, so go 3 over and then AUG, that's usually start, it's met, which tells us to start, and AUU, isoleucine, so I don't remember the code for that, so what I'm going to do is I'm going to come over here, isoleucine, and I want to figure out, isoleucine is ILE. ILE. So I can use these tables in conjunction. So UCC, so I come over UCC, C is serenine. And then if I'm not sure what that is, it's SER. UAU. 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 TYR. UUU. Let's double check our name on that. FEE. PHE, I'm sorry. CGU. GGU. GGU. Glycine. GL. Sorry, my kids are waking up. GCU. Alanine. And UAG is usually stop, I believe. So let's see. UAG is in fact stop. And that tells it to break it up. Okay. So ought to work. Not that difficult. Use those two sheets. The next one's matching these.
Quietly, I'm sorry. Hey, your school, I'm sorry. But you got a kitty behind your back.
I'm lucky I'm not getting eaten. Alright, so the next ones, we're matching. So I've got a series of different lipids here. And this is sometimes the hard part. So let's remember, this is glycerol. So if it's a glyceride, it's based off of that structure. And if it's a steroid, it's got that ring structure. So I'm going to start with, I've got the CH2CH. So this right here is my glyceride. And this, but it has phosphorus. And so the phospholipid has a glyceride with phosphorus. If it has phosphorus without that structure, for instance, when we go to this one, notice here, it doesn't have that glyceride. That's not A. We've got phospholipid. Here's that structure. My ester linkages. And that's, so this is my phospholipid. And I guess this is E. And that's E up there. Steroid is this distinct pattern. 1, 2, 3, 4 rings. Triglyceride. Now, we might be tempted to go here, but that phosphorus is more specific. Here's, again, my glycerol. So triglyceride, C. Now wax, very distinctive. I've got fatty acid and a long chain alcohol. There's my wax. So EADCB. Now let me go ahead and double check on my pretty pictures, which is not right there. Oh, you get them right. So hard part here then. You've got this that looks very similar, but the giveaway was right here. We got an amide, and so that is a sphingolipid. Notice all the rest of it looks exactly the same. So we've got to look for that glycerol, this OH there. That's what we were missing. Alright, the end of that document. Hey, we've done all the homeworks. Let's find the very last one of that. And EADCB. That's what we have. All right. And that wraps up our homework. All that's left is this thing. This is final exam terms. Whoa, man, look at all this. So let's get rid of some of that so we can see. Okay, I'm going to go through each of these real fast and we'll kind of review them. Alkanes, we say carbons and hydrogens, all single bonds. Alkenes, carbons and hydrogens, when you've got a double bond. Alkyne, you've got a triple bond. Cycloalkane, you've got a ring. Benzene ring, you've got the characteristic aromatic ring. Saturated versus unsaturated, so any kind of double bonds or rings. Eclipse formation versus staggered. Alright, so that's why we have our zigzag pattern. We're trying to avoid sterics. Aldehydes, alcohols, ketones. Be sure you're able to recognize each of those. Ether versus ester. Yep, gotta know those. Look for the presence of carbonyls. Really. Acids versus bases. Carboxylic acid derivatives. We had. So we're looking for not only our amides and our esters, but we're also looking at our anhydrides and our carboxylates and all kinds of acid chlorides, fatty acids, long chain carboxylic acids. Wax has an ester, so a long chain alcohol in the ester. Steroid, you've got the four rings you're really looking for. Amino acid, we'll just cover that here recently. So you've got alpha amino acids for all of these. Sugars, so we should be ready to handle those. Hemiacetal versus an acetal, so keep in mind. There's our hemiacetal. If we change that to a carbon, so it's two ethers on the same carbon, that would be an acetal. All right. So aliphatic and aromatic. So we know aromatic. So like benzene ring, unexpectedly stable. They have smell, a distinctive smell from. The name comes from the trees they come from. Aliphatic means not aromatic. Orthometapara, that came from our benzene rings and the substitution patterns, and I can't draw a benzene ring today. There we go. And so ortho meta would be 1, 3, and 1, 4 would be 1 pair. Alright, cis versus trans, okay. That's for our double bonds and for our rings. Condensation reactions, we lost water to make, so we did that when we were making ethers and when we were making esters. So hydrogenation, that's our reduction. So hydrogen gas, platinum, palladium, and nickel. Acid hydrolysis, that's where we split apart an ester. We can also split apart ethers using acid hydrolysis. Saponification is base catalyzed splitting apart esters. Right? Halogenation, so there you have to be careful. We're talking about, so we got two different halogenations. We've got the substitution where we had CO2 and light, or heat to light, and then we had our addition where we had halogenation that way. So hydrohalogenation, so this is most likely talking mostly about our addition. So hydrohalogenation was HX, and so we had to worry about Markovnikov, anti-Markovnikov, oxidation. So oxidation and reduction, you should know the three definitions of each. Combustion, fuel plus oxygen plus CO2 plus water. Zaitsev's rule, we used that when we were, so Zaitsev is making a double bond. So we want the internal double bonds are favored. Markovnikov's rule, the hydrogen, when we do an asymmetrical addition reaction, the hydrogen goes to the carbon with more hydrogens. Fischer projection, those are our up and down pictures like that. Hawthorne projection, that's where we drew the ring and we looked at it from the side. Alright, and we've got, so that's when we've got our hemiacetal linkage. Addition reactions, elimination reactions, D versus L. You also should know not only how to tell D versus L. D is on the right, L is on the left. You should know that sugars are going to be D and L. Sugars are D and proteins are L. Alpha and beta. So remember, if the CH2OH and then that OH to the right, that first carbon over there, if those are trans to each other, that's plan A, and if they're cis to each other, that's plan B. Right. Zwitter ions, positive and negative charges on the same molecule, but it's got a neutral overall charge. All right, enantiomers, mirror images, non-superimposable. Diastereomers, non-superimposable, but not mirror images. Meso, the compound contains an internal plane of symmetry. So that means that we can rotate it or flip it and we'll be able to make it superimposable. Alright, so enzymes speed up the reactions. What you know on the definition for organic carbon compounds, it contains carbon. Phenols have a benzene ring with an OH. Alright, a thiol, anything with an SH. Thioester, so carboxylic acid, carbonyl, with the S there instead of the O, so we're looking like that. Acid chlorides, same idea, with Cl. Acid anhydrides was this structure. Glycerides, so that's based off of glycerol. Then we had phosphoglycerides. So instead of having a carboxylic acid and ester bonds here, one of these is replaced with phosphoric acid. Sphingolipids, very similar to the phosphoglycerides, but one of these will not be this OH. Usually it's an amine there. So sphingolipids aren't glycerides. That's the key to that. Primary structures, just the order. Secondary structures, is it twisted into a helix? Is it in flat sheets? How is it coiled? How is it twisted? And then tertiary structure is that it's big loops when the rubber band starts to not just twist, but twist back around on top of itself. Quaternary structure contains information about its use. So, whew, got a lot going on there, a lot of terms. All right, so that takes care of our homework, and there we go. So we will catch you on the next one, and have fun.